our session for physical sciences. My name is Temba Ncube. Today we are focusing our attention on a very exciting section of chemical change, which has to do with stoichiometry. We're going to focus our attention on balanced equations and try to get a sense of what exactly does a balanced equation tell us about a particular form of a chemical change. And the word chemical change is actually, we'll use it in place of, chemical reactions. Remember, in a chemical reactions, we've got reactants and the products, and then what is very, very important in as far as a chemical change is that, or in a reaction, is that new substances are formed. So we'll look at the stoichiometric ratios in which substances react and try to derive a deeper understanding in terms of what exactly that tells us in terms of the quantitative aspects of that reaction. Now let's look at the overview of today's lesson and see where exactly how it actually fits into the broader quantitative aspects of chemical change. Right. This is our concept map. So the focus is on the quantitative aspects of chemical change. So stoichiometry deals with actually quantities, of substances that are evolved in a chemical reaction and would represent these chemical reactions using chemical equations. We would also, at a later stage in this very session, look into what has to do with the yield, which speaks to the amount of, product obtained. We would also express that as a percentage in terms of, the percentage yield. Right. Now, what exactly are some of the keywords that we need to pay careful attention to? The law of conservation of mass, which has a lot to do with, amount of matter that is concerned in a chemical reaction. We'll also use the term yield, which has to do with the, the quantity or the magnitude of the end product in a chemical change or in a chemical reaction. We'll also express that as a percentage in the form of a percentage yield. And then we'll talk about the theoretical, which has to do with what is actually expected versus what actually happens, which is the actual yield. So these are some of the key terms. But also remember, now when it comes to the terminology, this forms the basis. These are the tools of the trade. So in as far as the definitions, always draw your attention to the examination guidelines in terms of understanding what the definitions are. Pay careful attention to the keywords. These keywords must also be used in the correct context. Right. Okay. Now, chemical equations, that's our point of takeoff. When we talk of a chemical equation, sometimes we'd refer to it as a reaction. Okay, so a chemical reaction actually represents a chemical change or a reaction. So what I've indicated also in our opening remarks is that, the word chemical change it's used in place of a reaction. So immediately we talk of a chemical reaction, we are saying we've got reactants which are converted to products, and these products, they are actually they are made up of the elements that are in the reactants. So at the end of the day, if we start with A and B, on the other end, we must also have A and B. No matter the combinations will differ. So hence we'd say in any chemical change, new substances are actually formed. But these substances are actually composed of the elements that are making up our reactants. Right. Okay. So in a chemical reaction, we form new substances. This is what distinguishes a chemical change, a reaction, from a physical change, which we spoke of when we talk about, change of state or phase of matter. Okay. So when we talk about balanced equation, this is going to form a lot of, aspects of our discussion for today. This gives the mole ratio in which substances react. Now, the key is that when we talk about quantitative aspects, we're talking about amount of matter involved in a chemical reaction. So by all means, when we talk quantity, what is the SI unit? Okay, wait a minute. We spoke about the mole at one point or the other. So the mole becomes the standard international unit for quantity of matter. So we don't talk grams, we don't talk kilograms, liters. The SI unit is the mole, which talks about the amount of matter. So a mole is just a number. So we need also to try and recall that that's what the mole is all about. Okay, right. And then furthermore, when we have a balanced equation, you'll use these balanced equations. So some of these chemical reactions, they are not given in balanced form. So if we have a balanced equation, we can use this to calculate quantities, and also to determine the amount of reactant. So the moment we talk amount, think about the mole, okay, or the quantity of the products formed, okay. So quantitative aspects of chemical change have a wide range of applications in the economical production of chemicals. Now, why do we study quantitative aspects of chemical change? At some point or the other, we need to try and think about what are the real life applications of these concepts that we learn in class. Now, you also have to come to a point where you understand that when it comes to the real world, a lot of chemical reactions in the manufacturing industry are being carried out to produce these chemicals that are needed in, on a large scale. So the economic viability of that production process becomes very important, because it has far-reaching implications in as far as the costs, the energy consumption. So always think about that. So our understanding of the theory of what exactly happens when a chemical change takes place or a reaction becomes very, very key. Right. Okay. So we get to the law of conservation of mass. So these laws are actually part of the definitions that we listed in terms of the key terms, right? If anything is conserved, what does that tell us? It tells us that it remains constant. Whatever quantity is conserved, it remains constant. So if something remains constant, it means it doesn't change in magnitude or size, in amount, in quantity, whichever way you choose to actually look at it. So during any chemical reaction or a chemical change, matter cannot be created or destroyed, okay? So the number of atoms of the reactant is equal, so that's the key word, okay? Is equal to the number of atoms of the product. Let's put this into context. Suppose you start with substance X and Y. They react together to form XY. It's just a hypothetical reaction. Now, what happens is the amount of X and Y in the reactant must equal the amount of X and Y in the product. Also, it's very important that we emphasize that the products, they actually consist of the substances that are in the reactants. So if we start with X and Y, there's no way you'd end up with Z. So the product must consist of X and Y. So in terms of quantities, we are saying that whatever amount of these ingredients that you start with, okay, it should give you, the same amount of, of the products at the end of a chemical change or a reaction, okay? Right, so the total mass of all reactants, now we're talking to it in terms of mass, of all the reactants is equal to the total mass of the products. So if for argument's sake, we start with 50 kgs of reactants, at the very most, we must end with 50 kg of the products that consist of the elements or the substances that are in the reactant. So that's what the law of conservation of mass tells us. But it stems from the fact that matter cannot be created or destroyed, right? Okay, now let's look at a simulation in which we try and balance an equation, because the usual term that we use to apply the law of conservation of mass or law of conservation of matter is actually, we apply it when we actually try to balance a chemical reaction. So balancing is a way of ensuring that a chemical change or a reaction actually adheres to the law of conservation of mass, right? So we shall use a very simple example on a PhET simulation just to try and play around and see and discover some of the very important facts regarding balancing chemical equations, right? Okay, so if for argument's sake, we have a scenario whereby we want to make, let's say, ammonia. Now, the ingredients or the reactants, which are on our left-hand side, consist of nitrogen and hydrogen. Also pay careful attention. Let's start, say, for argument's sake, with 1 mole. Okay, so these are stoichiometric ratios that we are trying to make use of. Let's say we start with 1 mole of nitrogen gas. You'd immediately realize that the nitrogen is a diatomic molecule. So it exists as a diatomic molecule. So this nitrogen is essentially a molecule of an element. Why are we saying an element? Because it has got, two atoms of the same kind that are chemically joined together. If I draw attention to, the balance there, it says we've got 2, which is heavier than 0, okay? So on the left, we've got 1 nitrogen, okay? Let's also add another hydrogen, okay? So as far as hydrogen, it's also a diatomic molecule, okay? Now, the products that are formed, the product that is formed is ammonia. Ammonia is a molecule that consists of an atom of nitrogen and 3 atoms of hydrogen per molecule, right? So for us to balance, the number of atoms of nitrogen on the left must equal the number of nitrogen atoms on the right. That's the reactant and product respectively, okay? So what is it that we can do? On the left, we've got 2 of nitrogen, and then on the right, we only have 1. So for us to have 2 on the right-hand side, we need to increase the number of moles of ammonia, okay? Immediately we do that, you'd realize that the nitrogen is balanced, okay? So if the nitrogen is fine, then we need to do something about the hydrogen. If we focus our attention on the products in as far as the hydrogen, on the left, we only have got 2 atoms, which is a molecule of hydrogen, while on the right, there are 6 atoms of hydrogen. So to balance this, how exactly are we going to do that? It means we need to increase the number of molecules on the reactant side so that the scale will tip more to the left, and with the hope that we would establish some form of balance. Now let's include another molecule of hydrogen. Is the balance there? Have we achieved balance? Definitely not. Why? On the left we've got 4. On the right we've got 6 atoms, okay? Or moles of, let's use the mole, the 10 moles, okay? So for us to balance that, we need to include another one. Now, there's a happy face, okay? What is it that we derive here? The number of moles of nitrogen is 1, is to 3, is to 2. So what does this tell us? It tells us that 1 mole of nitrogen reacts with 3 moles of hydrogen to give us 2 moles of ammonia. That's why the scales are balanced, okay? So that's the main idea in as far as the balancing act is concerned, right, okay? Now let's look at the interpretation of a balanced equation of reaction and try to understand what exactly it tells us about the chemical change. So what we managed to understand from the balanced equation of reaction is that a mole of nitrogen gas reacts with 3 moles of hydrogen gas to give us 2 moles of ammonia. So the stoichiometric ratio in which these substances actually react with each other is 1:3:2, right? So that's the stoichiometric ratio. So remember, why are we saying it's the stoichiometric mole ratio? Because everything is about the mole, and what we know about a mole is that a mole of any substance contains the same number of particles, be it ions, be it molecules. So because here we're talking about molecules, it means then we can therefore say that the stoichiometric ratio in which these substances react with each other to form the product is 1:3:2, right? So that's as far as the equation is concerned. So the application in as far as balancing equation, you'll be given a lot of different types of equations, but the art of balancing or the understanding of how we carry out the balancing process is very important. So a lot of practice, I think, it will be demanded from you to try and familiarize yourself with saying, okay, here we're talking about the whole number ratio in which these substances react. And what exactly does a balanced equation of reaction tell us? It tells us, very, very important, that this is the mole ratio in which these substances react with each other to form the products. Having said that, let's take a short break. When we come back, we'll look at something on the percentage yield in terms of the reactants and the product. Let's take a short break for now. welcome back to our second segment. We're still looking into the quantitative aspects of chemical change, but our focus for now is on percentage yield. We want to get a sense or some form of understanding in the sense that, when reactants react with each other, there's what we expect in terms of the yield, or the end product, in as far as the quantity. Then we want to check as to what percentage of the actual, of the theoretical yield is what we get at the end, which is the actual yield. So when we talk about yield, loosely, I think we are referring to the amount of product. Okay, so based on what we put in as far as the reactants are concerned, right? So our focus for now is on yield based on the balanced equation of reaction. Okay, so that's the whole idea on stoichiometry, right? Okay, so the mole ratio in balanced equation, what does it tell us? It tells us that, in stoichiometry, it involves the study of numerical ratios in which reacting substances participate in a reaction. And here it's not just the ratio, it's actually the mole ratio, right? It tells us the mole ratio. Why the mole? I think we've overemphasized the fact that the mole is the SI unit. So, if we talk quantity of a matter or quantity of a substance in a chemical reaction, we shall draw attention to the mole. So the ratio between all substances that are part of a reaction which has reached completion, that's a very important term, is called the stoichiometric ratio. So when you react two reactants, let's go back to the example of the formation of ammonia when nitrogen and hydrogen react. So when we say that the reaction has reached completion, what do we mean? We're saying that the reaction has stopped in the sense that one or both of the reactants has been used up. So once we don't have all the reactants present, then the reaction stops to happen. I think it's logic. Then by that time, we would say, okay, either one or both of the reactants has reacted completely. Okay, so that's how we describe the end of that reaction, by using the term completion. Okay, it's a very important term that will have a lot of implications going forward. So that's as far as completion. Now let's look at percentage yield. Okay, so the theoretical yield, right? I'll underline that because that's a very key term in terms of what happens in a chemical reaction. So theoretical yield is the maximum, so that's a keyword, amount of product formed as calculated from the balanced equation of reaction. Okay, so remember, first things first, the balanced equation gives us the stoichiometric mole ratio in which substances react with each other to form the products. So when that happens, we are simply saying that we are able to determine, this is what we expected. That's the maximum in terms of theory, should the reaction reach the end when one of the two reactants has been used up or both. Okay, now that's the theoretical yield. So in real life or in practice, the actual yield is usually less than the theoretical yield. This is the reason behind that, is that not all reactants are actually converted to products. So there is a comparison between actual yield and theoretical yield. Okay, so in most cases, what we get is not actually what we calculated theoretically. This is what we would expect. Okay, so theoretical yield is what is expected. Okay. So this is the expected amount of product, okay, as per the balanced equation of reaction. It can be product or products, it doesn't matter, okay? So it will depend on the context under consideration, okay? And then, so the percentage yield, in the percentage yield, the actual yield can be used to determine the large-scale production of important chemicals, if it is viable or not. So we have our own expectation in terms of the quantity of the product, but in reality, the actual yield is normally less than the expected or the theoretical yield. So, in terms of application and the practicality of, the importance of percentage yield is that if, large-scale chemical production is to take place, in industry. Now, there is as a measure of how economically viable the process is, we have to determine, the percentage yield, which says, okay, this is what we produce, this is what we versus what we expected. Is this profitable? Is it economically viable? Are we using the cost attached to it? Has also those far-reaching implications. So we need to think about that in as far as the application of, percentage yield as a measure of, economic viability of a process that is being carried out in a chemical reaction, right? So how do we calculate percentage yield? Percentage yield is actual yield. This is what we get in reality over the theoretical yield multiplied by 100, because remember, anything that is expressed as a percentage is measured against 100%, okay? So actually the percentage yield would be, in practice less than 100, okay? Right, so here is an example of percentage yield type of a problem. Okay, iron metal is extracted from iron 3 oxide according to the following equation. Okay, take note, this is iron 3 oxide. Iron is a transition metal, so we know from our chemical formula that the iron in this case is 3+, okay, because we're told by that number, it's an indication of the charge or the oxidation number. We'll talk about that later, okay, and then oxygen 2-, which gives us the formula Fe2O3. So that's the oxide of iron. Okay, this oxide reacts with carbon monoxide to give us iron metal and carbon dioxide gas. So the process involved here, our main product of interest is the iron, okay, metal. So we want to extract iron from its ore, okay. So that's the equation, okay. Now the question is, what is the theoretical yield of iron if 150 grams of the ore reacts completely? So if it reacts completely, we're saying if this reaction reaches completion, what is our theoretical yield? So we're going to use the stoichiometric ratio in which these substances react to try and determine that. But before we do that, first of all, we need to actually calculate actually balance the equation, right? So in balancing the equation, that's the first step, okay? How many atoms of iron do we have on the left? It's 2, okay? So for us to balance, if we put a 2 there, it looks okay for iron for now. And then if we go to carbon dioxide, okay, carbon monoxide versus carbon dioxide, because both of them, they actually contain carbon, okay? Because our focus is not so much on the balancing, but balancing becomes an important part of our problem solving. So if we have, let's say 3 here, and then also another 3 there, let's check if it's balanced. How many ions do we have on the left? Is 2, on the right is 2. Let's go to carbon, 3 on the right, and then oxygen, we've got 6, 3 plus 3, and then 6. So the stoichiometric ratio in which these substances react with each other is 1:3, 2:3. So that's the stoichiometric ratio in which they react with each other. So the question, if we can go back, it wanted us to calculate the theoretical yield of iron if there is 150 grams of the ore. This is the ore that we are talking about, the iron 3 oxide. Now let's look at the conversion of the mass into the SI unit, which is the mole. So the stoichiometric ratio in which they react with each other is actually 1:2. Okay, this is the ratio for the ore to the iron. So we are told that there is 150 grams of the oxide, okay? So if there is 150 grams of the oxide, we ask ourselves, in 150 grams, how many moles of iron 3 oxide are present? So we know that number of moles of iron 3 oxide is it actually equals to the mass of the sample divided by the molar mass. So the mass of the sample in this case, we are told is 150 grams, okay? Now the molar mass of iron 3 oxide, if you go back to the periodic table, you'll get 160 grams per mole, okay? So if we go to our calculator, just to check the calculation there, we'll have 150, that's the mass of the sample, divided by the molar mass, which is 160 grams per mole. This gives us, as a decimal fraction, 0.94. So in other words, what are we saying? We are saying that in a 150 gram sample of iron 3 oxide, there is 0.94 moles of the oxide, all right? So that said, it means that the number of moles is equals to 0.94 moles, right? Now, what do we know? We know that a mole of iron 3 oxide produces double the number of moles of iron. So the number of moles of iron in this case, which will be formed, is equals to, you know, the double that, which is 2 multiplied by 0.94, okay? Which is 2 multiplied by 0.94, right? So the number of moles of iron that will be obtained, okay, from the stoichiometric ratio is, if we go back to our, so it's 0.94 multiplied by 2. This is the number of moles, which is 1.88. So there's 1.88 moles of iron, okay? 1.88 moles of iron will be formed, right? Okay, so what's our next step after that? Step number 3, we can calculate the number of moles of the substance. We've managed to do that. We say number of moles of the product is equals to 1.88 moles. Okay, so where did this come from? It came from the stoichiometric ratio of a mole of the oxide produces 2 moles of the iron. So that is straightforward. Okay, what is the next step after that? We want to calculate the mass of the substance, okay, based on the stoichiometric ratio. What do we know? We know that a number of moles of iron is equals to mass of the iron that will be formed divided by the molar mass, right? So what do we have now? We've got the number of moles, which is 1.88, right? This is equals to the mass, the mass in this case, we just want to check what is the mass of the iron, okay? This is what we have to get at the end. So we are saying that we are looking for the mass of the sample that will be formed divided by the molar mass of the iron. So the molar mass of iron, atomic mass, is 56 grams per mole, okay? But remember, the stoichiometric ratio is still 1:2. So here it's, we'll have our mass is equals to the number of moles, which is 1.88, multiplied by the molar mass, which is 56 grams per mole. So what we get here is the actual mass of iron that will be, the theoretical mass of iron that will be formed from, you know, the stoichiometric ratio. So if we go back to our calculator, what do we have? We've got 1.88, which is the number of moles, multiplied by 56 grams per mole. So what we'll get here will be the mass in grams of what is expected, okay? So what do we get there? As a decimal fraction, it's 105.28, okay? So the mass is actually 105.28 grams, okay? So that's how we determine the mass of iron. So this is the mass of iron theoretically that must be formed, right? Okay, so in terms of, you know, calculations, we are able to say, okay, if this is the number of moles in which these substances react, we'll use that stoichiometric mole ratio to actually determine, you know, the theoretical yield. So theoretical yield is actually what is expected. But in reality, if we go back to that question very quickly, where we are told that at the end, before we looked at those steps, it says if the actual yield is 87.9 grams, what is the percentage yield? So we must express this as a percentage of the theoretical yield, okay? So this is 87.9, okay? So if we go back to that, we have 87.9 is the actual, okay? Actual yield is equals to 87.9 grams, okay? And then theoretical is what we calculated, Okay, so our theoretical yield is what we calculated. If we go back, that value is 105.28. So that's what we expected, 105, okay, 0.28 grams. So percentage yield in this case becomes actual yield, which is 87.9 divided by 105.28, okay, that expressed as a percentage. So our percentage yield in this case would become, if we go back to our calculator, it will be, in this case, 87.9 divided by 105, okay, 0.28, right? That, then we multiply this by 100. It gives us the percentage, which is 83.49%, okay? So that's 83.49%. So this is how we managed to determine the percentage yield of this extraction of iron from the ore. So that's how exactly we carry out, you know, calculations as an example based on percentage yield. When we come back, we'll look at more problems in terms of the yield and, you know, percentage yield. Let's take a short break for now. Welcome back to our third and final segment. We're still looking at percentage yield. Now we'll focus our attention on a different example altogether and see how exactly we know what's the approach in terms of solving problems that involve percentage yield. Right. So we're still talking balanced equations, but our focus is on the yield in this case. That's as far as stoichiometric calculations are concerned, right? So here we've got a scenario that says methanol, CH3OH, that's the molecular formula, that's the name of the substance, can be burnt in oxygen, okay, to provide energy, or it can be decomposed to form hydrogen gas according to the following equation. As to whether the equation is balanced or not, it's something that remains to be seen. However, take note that this is a decomposition type of a reaction, okay? So according to the equation, if you look at it in terms of carbon, okay, there's one carbon on the left and one on the right. Okay, oxygen is fine. If you look at hydrogen, there's 4 on the reactants, and then there's 2 on the product. It means in terms of balancing, then this will be 2. So the stoichiometric ratio in which they react is 1 methanol is to 2 hydrogen is to 1 carbon monoxide. Now we are told that that mass, which is 125 grams of methanol, is decomposed. We are interested in determining the theoretical yield of hydrogen gas, right? So our focus will be on methanol to hydrogen. So in terms of stoichiometric ratio, we'll look at those 2 to be precise, right? Okay, so the balanced equation, we said here there's 2 moles. So the stoichiometric ratio in which they react is 1 is to 2, right? So we are told that there is a sample of 125 grams of methanol, okay? Now, what is the theoretical yield of hydrogen? Now, the theoretical yield is what we expect in terms of the stoichiometric ratio, in that these substances react to form the other. So as a result, we'll look at, let's change this mass of 125 grams into moles. Why the moles? Okay, the question that is very important to us is that, okay, remember, the mole is, the SI unit of quantity of matter. So when we talk amount of substance in a chemical change or in a chemical reaction or in stoichiometry, so the mole is our point of reference. Now, we ask ourselves, in a 125 gram sample of methanol, how many moles of it are present? So number of moles of methanol, which is CH3OH, right, is equals to the mass of the sample divided by the molar mass, okay? Now, the sample mass is given as 125 grams, right? 125 grams. The molar mass of methanol is 32 grams per mole. Where did we get the 32? Carbon is 12 plus hydrogen, which is 4, which is 16, plus another 16 for oxygen. That gives us 32, okay, grams per mole, all right? So whatever we're going to get here in terms of the number of moles of methanol, CH3OH, okay, is equals to that. So if we go to our calculator, you'd immediately realize that, okay, so in this case, what do we have? We've got 125 grams divided by 32 grams per mole. This gives us that as a decimal fraction is 3,91. Okay, so how many moles of methanol are present in 125 gram sample? It's 3,91 moles. Okay, so this gives us 3,91 moles, right? Now, if 125 is the mass of the sample, now every mole of methanol gives us double the number of moles of hydrogen. So in other words, number of moles of hydrogen based on the stoichiometric ratio is 1:2. So it's going to be 2 times the number of moles of methanol. So it's 2 multiplied by 3,91, right? So the number of moles of hydrogen gas, okay, according to the stoichiometric ratio is equals to, if we go back to our calculator, so that's 3,91 multiplied by 2. What do we get? It gives us 7,81. So it's 7,81 moles, all right? 7,81 moles, okay? So that's the number of moles. But the question asked us to determine the theoretical yield. It should be actually the mass, okay, in grams. So we need to change those moles back to the mass. So we know that number of moles of hydrogen gas is actually equals to mass of hydrogen over the molar mass of hydrogen. Okay, so now we have the number of moles of hydrogen that will be formed from 125 gram sample. So this will be 7,81 is equals to the mass over the molar mass of hydrogen, which is 2, okay? The molar mass comes from that formula. Take note, we do not multiply by the coefficient in this case, which is the stoichiometric ratio, because the coefficients, they simply give us the stoichiometric ratio in which they react. So the mass is equals to 2 multiplied by 7,81, right? So if we go back, this 7,81 multiplied by 2, okay, this gives us the actual mass of hydrogen. So the theoretical yield is that the actual mass of hydrogen that will be formed is equals to 15,6 grams, 625, okay? So it's 1615,625, okay, grams. This is what will be formed in terms of hydrogen gas. So we can say the mass of hydrogen gas that will be formed is exactly that. But then the question that follows up, it says we must be able to determine the percentage yield. Now we want to express the actual yield. This is the actual yield because it says only 13,6 grams were formed, okay, of hydrogen gas. But what did we expect? The expected amount was 15,625, okay? So if that's the case, we would say, okay, this is a percentage yield, okay, is equals to the actual yield, which is 13,6, okay, divided by the expected one, which is the theoretical. In this case, the theoretical is 15,625, okay? So that's 15,625 multiplied by 100. That will give us the percentage yield. So our percentage yield in this case would be, okay, 13,6, right? 13,6, which is the actual yield divided by 15,625, okay? Equals to multiply that by 100. It will give us the percentage. So our percentage is 87,04, okay? So this is 87,04%. So always leave your answer in 2 decimal places, right? Okay, now we've got another typical example, right, which says in the reaction below, this is the one for formation of ammonia, which somehow looks very familiar to us, okay? In the first segment, we managed to do the balancing act using the simulation. So we're told that there's 30 grams of nitrogen which react completely to form that amount of ammonia. So this 26,6 is the actual yield, okay? This is the actual yield Okay, that's what was obtained in practice, and then it was obtained from 30 grams of nitrogen. So we want to calculate the percentage yield of ammonia in this case, right? So we would ask ourselves, is the equation balanced? Yes or no? It's definitely not balanced, because we remember from the balanced equation, it's 1 mole of nitrogen is to 3 moles of hydrogen is to 2 moles of ammonia. So we need a 3 there, and we need a 2 there. Okay, so that's the stoichiometric ratio in which they react with each other. So the question that follows is, for us to get the percentage yield, we need to find the expected yield first, which is the theoretical, to say if there is 30 grams of nitrogen that react completely, of these 30 grams, how much do we get in terms of ammonia? So the first question, the first part of our problem solving has to do with how many moles of nitrogen are present in the 30 gram sample of nitrogen gas. So number of moles of nitrogen gas, okay, is equals to mass of sample divided by the molar mass, okay? So the mass of this sample is 30 grams, okay? So we've got 30 grams, okay, divided by the molar mass of nitrogen gas. Each nitrogen atom has a mass of 14 grams per mole. If so, it's a diatomic molecule. This gives us 28 grams per mole, okay, from the periodic table of elements. So how many moles of nitrogen are present in that? So we can quickly determine that, right? So what do we have? We've got 30 divided by 28. Okay, this is the actual number of moles, so which is 1,07, okay, 1,07 moles. All right, okay, so that's the number of moles of nitrogen. But then how many moles of ammonia must be formed? Okay, every mole of nitrogen forms double the number of moles of ammonia. So from the stoichiometric ratio, we know that number of moles of ammonia in this case, okay, will be equals to 2 multiplied by the number of moles of nitrogen, which is 1,07, right? So this gives us, if we double that, what do we get? Okay, we'll multiply that by 2, we'll get, okay, 2,14 moles, okay, 2,14, right? So this is 2,14 moles. Now the next question is, in 2,14 moles, what's the actual mass? Let's change these moles into the mass so that we get the actual yield, the theoretical yield. So what do we have? We know that number of moles of ammonia, right? Number of moles of ammonia is equals to mass, okay, divided by the molar mass. So we've got the moles in this case, which is 2,14. So 2,14 is equals to whatever mass we'll get. The molar mass of ammonia is what we need. It's 17 grams per mole, okay? 17. So the mass that is we're going to get is 17 multiplied by 2,14, right? Okay. So we'll multiply this by 17 to get the mass of ammonia, which is 36,42, okay? So this is 36, right? Okay, if we go back, this is 36,12. Okay, let's just go back to that so that we get that. So the calculator gave us a value of, just to verify that, 36,43, okay? So the mass is 36,43, okay, for 3 grams. All right, so if we want to get the percentage yield, because that's the question that it asked us, okay? We want to get the percentage yield. Let's use those values then. So the percentage yield of ammonia, okay, is actually equals to, you know, the actual yield. So if we look at the actual yield is 26,6 grams. That's what was formed, okay? So it's 26,6 grams, okay? This is the actual. What did we expect? That's our theoretical yield. Our theoretical yield in this case is 36,43, right? So that's 36,43. We multiply this by 100. it will give us the percentage yield of ammonia. Okay, so if we can quickly verify that from the calculator. So we have the calculation in terms of 26,6, okay, divided by the theoretical yield, what we expected, okay, the one that we calculated from the stoichiometric ratio. So this is the actual yield, okay, just to go back. So this is the actual yield, okay. This 26,6 is the actual, okay, yield. This is what was obtained, okay? And then this is actually our theoretical, the one that we determined from the stoichiometric ratio. So this is our theoretical yield, right? Just to put things into perspective. Then this gives us, if we go to our calculator just to verify that. So it's 26,6 divided by 36,43, right? Okay, we multiply that by 100 so that we get that percentage. So the value as a decimal fraction is 73.02%. Okay, so it's 73.02%. So that's the percentage yield of ammonia, right? Okay, so in closing, what are we saying? The mole is the SI unit of quantity of matter. Okay, just to drive that point, you'd realize every time we were given the mass of sample of a substance, we had to carry out calculations to express it in terms of the mole, because the mole is the SI unit, and we can compare moles and moles, you know, so that's why we had to convert the mass of each sample into the moles, okay? And then the balanced equation gives us the mole ratio. We want to emphasize on that, in which these substances react with each other. And in any chemical reaction, the total mass remains constant. So this is the law of conservation of mass, right? Okay, and then also when it comes to the theoretical yield, we understand that this is the maximum amount of product that is expected as calculated from the balanced equation of reaction, which is why we always balance the reaction. And then the actual yield is used to determine the large-scale production of chemicals and to check whether the production process is actually viable. So a higher percentage is an indication that, yes, indeed, the production process is economically viable, okay? So that's how we calculated our percentage yield of a substance, right? So having said that, I think we managed to put these two pieces together in terms of how then do we use the stoichiometric ratio to determine or to predict, you know, the amount of substance using the mole, which is the SI unit. So that those are some of the very, very important, you know, aspects of our discussion today. So in a nutshell, the mole is used to determine, you know, any quantitative aspect of any reaction. Why? Because the mole is the SI unit. And then we can do all these calculations, but we must base our understanding on the importance of how a chemical reaction takes place in terms of quantities. Having said that, this brings us to the end of our session. Cheers and bye-bye for now.